Welcome everybody to this second session this afternoon in room 1, sorry. And this is the separation session. We have 3 presentations for you. And the first, they're all about conflict resolution. So separation is really about the task of separation, not the minima or the specs, but really the task of how to do it. A lot of AI and machine learning, so it's going to be an interesting session. The first presentation will be done by Mudhakar Srivatsa. He's a research staff member at the Distributed AI Department in IBM's Watson Research Center, TJ Watson Research Center. And his work is focused on machine learning on large-scale spatiotemporal data generated by moving objects, ranging from smartphones, cars, ships, asteroids, and airplanes as well. This is what we will be talking about today. If you could share your screen, Mudhakar, and then we can hear your presentation titled Towards AI-Based Air Traffic Control.
Are you able to see my screen?
Yes, and it's also slideshow mode. Good luck.
Yes. Okay, wonderful. All right. Thank you for that introduction. But yes, there is, as the session chair introduced me, yes, there is additional work on asteroid tracking and collisions between asteroids as well, separation loss between asteroids, which is a separately interesting piece of work. I'll be happy to discuss that offline. But the main purpose of this call was to look at how AI can help with air traffic control. This is joint work with LFV, the Swedish Civil Aviation Administration, and with the rest of with several other folks from IBM Research in New York. The basic problem statement, I think, is very well known to the audience here, but really the problem statement is very simple. We have to direct an aircraft through a controlled airspace as safely and as efficiently as possible. That really is the task at hand here. In this process, the total load that is there on the air traffic controllers is increasing year on year quite a bit. Again, large increase in both passenger and freight traffic in the last few years, even accounting for some of the recent loss in traffic due to COVID. And it is also estimated by the FAA in the US that when we start counting drones flying above a particular altitude as flying in controlled airspaces, the volume of this in terms of number of flying objects that we need to handle can increase potentially by 10x, at least in cities, for example, where we do expect a lot of this drone traffic to be present. So the problem scale is going to increase year on year, and hence the question becomes, how can we help automate portions of air traffic control? Even if the process is not fully automated, can we be an agent assist? Can we give recommendations to an air traffic controller along with sufficient level of explanation, counterfactual explanation, and I'll sort of explain the difference between the two of them subsequently. How can we provide the sufficient level of explanation and counterfactual explanation so that the decision maker, the air traffic controller, can make the choice? That really is the broad goal here. So the way we go about modeling this is loosely speaking a form of reinforcement learning problem, where we look at the current state of the aircraft. Unsuspectingly, the current state includes latitude, longitude, altitude, ground speed, the direction of travel azimuth, and the rate of ascent or descent in case the aircraft is ascending or descending naturally. So that's the instantaneous state of the aircraft. There is also things that go beyond this, like a flight plan, which includes a sequence of waypoints in the future that the aircraft has to traverse. And if you are ascending or descending, there is generally a target altitude. So you're ascending to say 30,000 feet or whatever be the target altitude. And there are certain amount of static attributes associated with the aircraft as well, things like body type, whether it's like a 747, it's a smaller aircraft, payload, fuel level, how late the aircraft is, because again, when you are trying to make a planning decision for routing this particular aircraft, all these things are important. But the main focus of this particular talk is going to be almost entirely safety based. So we have what we call as a white box AI model. White box AI models generally give high levels of explainability and control for path planning for these aircrafts, paving way towards some future work into black box AI models for improving the efficiency of the paths that we are taking. So safety first, of course. So separation loss is the primary objective here. There is a minimum amount of empty space that needs to be around a specific aircraft. So as per FAA regulations, 1,000 feet altitude separation, 5 nautical mile longitude latitude separation if you are on the same latitude. And of course, these things are subject to change. There are geographical polygons, no-fly zones. There are areas affected by bad weather and so on. Again, some of those considerations are downstream considerations which are not actively factored into the current planner that we are discussing in this talk. So what are the remediation actions that one can take? There are basically 3 remediation actions. One is a change to ground speed, change to the azimuth, the heading, or the change to the altitude, right? Those are the 3 primary actions that we take. But there are several important things that we have to remember. That things like slowing down will, of course, impact arrival times. When we have an azimuth or a heading change, there needs to be a follow-up action to bring the aircraft back on the correct course. And there are, of course, efficiency considerations like higher fuel burn rate at lower altitudes. And these actions, whether it is altitude or azimuth or ground speed change, can take non-zero amount of time or will take non-zero amount of time. And there is a human element to this in terms of how many instructions we can relay, how many actions we can relay to the pilot at any given point in time. So there were restrictions imposed in the form of no more than 6 actions per minute that can be relayed to the cockpit. So these were all some of the considerations that were explicitly taken into the picture when we are doing action recommendation for the aircrafts. So let's look at first some of the enabling tools and considerations. Here, there are offline models that one can build using ADSB data, which is automatic surveillance broadcast, which every aircraft does roughly every 10 seconds, once it's at the cruising altitude, perhaps at a much higher frequency when it's on ascent or descent. So there is some of this data available to us that can be used into the modeling. Second, there are high fidelity simulators. In this particular case, we rely upon the NARSIM simulator for some of our planning purposes. So really the actions that we are taking are all relayed to the simulator so that the simulator can take the action, and we continuously track the updates to the state space, updates to where all the aircrafts are located in the airspace as time proceeds. Of course, there are aspects that need to be considered. For example, we might ask for an aircraft to turn by 5 degrees, but it may only turn by 2 degrees. So there is a continuous feedback and a follow-up loop that is in place in the planner, which when given an action, even if the action is acknowledged, there is continuous monitoring to see if it is faithfully followed. And if it isn't faithfully followed, suggest a next action, which may be larger than 5 degrees because 2 or 3 minutes have passed since I recommended the 5-degree turn action. But 2 or 3 minutes later, maybe I need a 10-degree turn if the action has not been taken. So there is a continuous feedback and a follow-up loop here that monitors all the aircrafts and suggests best action at this given point in time. Now, we have paid specific care to explainability. This is a favorite meme from the philosophy department. Why are you here? But really the question is, why take a specific action? And we do focus on 2 forms of explanations. A, why take action? Why turn left by 5 degrees, for example? And counterfactual explanations, which is why not take a specific action, which also becomes very important to sort of give the confidence to the air traffic controllers that the AI system is doing why it is doing. If the ATC, air traffic controller, feels there is a better action, we should also be in a position to explain why we are not recommending that better action to the best knowledge of the AI planner in this case. So we do support both forms of explanations here grounds up, so that when we recommend top 3 actions, the actions come with explanations why we are taking the action. And it is also possible for us to explain why we are not taking specific actions, either in an interactive mode or a certain set of pre-canned actions. We can always try and explain why we are not taking some simpler actions than what we are recommending. And finally, risk averseness is a key factor here. Essentially, safety first is the goal. Safety in this case is enforced using a white box AI model, which what it means is that these are physics-based models with the AI planner. But the physics-based models are accurate as far as the modeling assumptions are made. So for example, we operate on an ellipsoidal Earth. So the models as far as the future states of these aircrafts are accurate as per the ellipsoidal Earth approximation that we are making. So under the boundaries and constraints of the model, there will be no coin toss, no inaccuracies introduced to say that why was this particular action taken, because it's all done in a white box mode. There is a notion of provability under the assumptions, of course, that the white box model is making. A lot of the efficiency considerations are often done with a black box model, meaning there is a lower level of explainability that a black box model will offer. It is not the same level of provable explainability that a white box solution can give you. But if safety is already satisfied by a white box model, and I know 3 actions are safe in terms of avoiding separation loss, the optimality between those 3 known safe actions could be done at a lower level of explainability, which is what the black box model is used for. So we intentionally structured this AI planner that we use for air traffic control as a combination of this safety white box AI model for safety, and you can call it as a black or a gray box AI model for efficiency. So by design, separation losses are provably explained as per a mathematical model, but the optimality choices can be made using a more exotic black box model. Okay, so those were the main sort of tenets that we sort of laid out thanks to all the help from practitioners in the space. We were able to sort of formulate the problem as follows. Okay, so really, what is the goal of AI-assisted air traffic control? This tight feedback loop that we spoke of. There could be historical simulation data, ADSB data, and RSIM simulations that can be used here. This tight loop really is, AI monitors the real-time airspace. Airspace data is fed into AI. We provide a list of course of action recommendations, a ranked list of course of action recommendations with explanations, which then the ATC operator can validate some of them and feed them to the pilot. The pilot may or may not accept the change. When they accept the change, they may or may not faithfully execute the action, hence a tight feedback loop. What are the key components of the solution architecture? So it's the solution is a cloud native solution, can be something that's realized on premise as well, where we can have a lot of these logs coming from aircraft performance data, the live simulation data going into object stores and cloud databases. And on the top, you find the main portion of the closed loop AI system, which basically works on 2 inputs today, which is the radar track events and the flight plan. There is a STCA, which is short-term conflicts that the simulator identifies, which are primarily used for validation, but not for planning. So radar tracks, flight plans are used for planning. Currently, no-fly zones and things like that are not factored into the plan yet, but there is plans in the future to include them in the AI planner. So today we work on radar track and flight plan, and then we recommend the next action, and the action gets fed to an RSIM simulator. And really, the system is designed such that we can have multiple RSIM simulators running. So I don't have to operate on one scenario. I can operate on N scenarios in parallel and do AI planning on N scenarios in parallel. Okay, Slightly deeper dive here. So we do get a continuous stream of log lines from NARSIM, which can be one of these 4 kinds of events: the short-term conflict, the radar track, the flight plan events. So we obtain the flight state from here. We have a very high-speed encounter detector, which is based on a physics or a mathematical model for detecting separation loss between aircrafts, typically next 20 minutes into the future. Once an encounter is anticipated, the auto planner kicks in to recommend course of action. The actions are ranked and they are sent back to NARSIM in terms of an action. Now, how are we, one level below, how are we handling these steps, right? So we sort of model and forecast a 3D track of the aircraft over the next typically 20 minutes. These are modeled as 3D piecewise line segments. On the lat-long plane, these are arcs, these are elliptic arcs. You might be very familiar with great arcs, which are shortest point between 2 points on a sphere. Elliptic arcs are an extension from great arcs to an ellipsoid. So the line segment is an elliptic arc on the lat-long space and a smooth ascent or descent on the altitude space. So an example of a piece can be an ascent can be a contiguous 3D line segment, a descent can be one. Your heading to the next waypoint can be one contiguous 3D line segment and so on. So you can think of the future track as a sequence of these 3D line segments. For very fast encounter detector, we use a 2-dimensional spatial index on the latitude longitude space to look for 5 nautical mile separation loss between aircrafts. Then we look for altitude separation because sometimes you may be within 5 nautical miles, but there could be sufficient altitude separation. Then we have a physics-based model which is doing fixed point iterations on the specific trajectories to look for separation loss. Because when I look at a 3D track, the entire 3D track is treated as a geometry, but in reality, the aircraft is at different points on this 3D track at different points in time. So the initial 2-dimensional test is working on the whole geometry, the entire track, as if it's a single geometry, to again identify possible encounter losses, but with false positives. So the false positives are first pruned using the altitude test and then pruned using fixed point iterations on the exact trajectory that the aircraft follows. So these encoders are meant to be running in real time at very high speed. For example, all of Northeast US entire 1 day's traffic can be processed through this pipeline in about 2 hours to detect encounters between any 2 aircrafts. The more interesting piece I want to focus on here is the action recommendation. So once we know an encounter is happening, we model the action as a lattice. So basically an action is a quanta of change in the ground speed, quanta of change in the azimuth, quanta of change in altitude. The minimum quanta for ground speed is 0.01 Mach, azimuth is 5 degrees, altitude is 1000 feet. Of course, they can all be changed based on what we think is better suited. When we work in this domain, the action space becomes what is known as a lattice. 0, 0, 0 essentially means 0 quantas of change in all the 3 dimensions, meaning don't take any action at all. At the top, let's say there is 533, which means 5 quantas of change in ground speed. So 0.05 Mach change in ground speed, 3 quantas in azimuth, so 15 degrees, and 3 quantas in altitude, which could be 3000 feet plus or minus in all of them. So the action space gets modeled as this lattice. And what we are essentially doing is a white box model of AI, which is pruning the state space to determine which action, as we traverse this lattice in a breadth first manner from bottom to top, which action can resolve the separation loss. There are some rules that we use for pruning the lattice, such as dominance relationship between 2 actions. So for example, if 001, 1 unit of altitude change solves the problem, I don't need to do 2 units of altitude change. So I don't need to explore 002, for example. Those pruning rules are better explained in the paper so that the AI planner can very quickly explore thousands of possible actions in hundreds of milliseconds essentially. So here is an example. If 001 succeeds, every lattice node that dominates 001 can be pruned from the search space, and only attention is paid on the remaining portion of the search space. So what we have here is that for every aircraft, we can sort of give instructions ultimately to the simulator LFV 906, for example, turn right to heading 70 degrees. So we can give these instructions. We do handle both two-way and multi-way conflicts between aircrafts. So two or more aircrafts can simultaneously be involved in a future conflict. So we can sort of resolve and provide actions for all of them. We also pay attention to the fact that I cannot give instruction to an aircraft that has not entered my sector. So while we are tracking aircraft that are outside the sector, we do realize that the earliest time I can give an action to an aircraft is when it enters the sector. So we do take that into consideration when we are exploring the action space. Finally, as a future step, what we can do here is black box efficiency. So when we sort of get these white box models recommending these set of actions, what we can do is determine the best possible action using a black box model. So for example, we can feedback the lateness of the aircraft. We can feedback estimated fuel consumption based on the altitude at which the aircraft has been flying for the rest of its track, and use that as a metric for optimization for the black box AI model, which can then pick the best safe action that the white box AI model has recommended. Some very quick look at some of the evaluation results here. We did about 10 runs on normal sector load, each run lasting about 2.5 hours. And we measure things like how many predicted conflicts were detected, how many instructions were sent to the aircrafts. Was there any separation loss encountered even after we sent those clearances? Did we send more than 6 clearances per minute? Did we make the track inefficient? So any number you see more than 1.0 means we made the route inefficient vis-a-vis the original flight plan. So numbers that you see below 1.0 means we in fact made the route more efficient compared to the original flight plan. And how many instructions of which kind were given? Ground speed instructions, heading change instructions, and were these instructions large in magnitude, small in magnitude? So these were all measured in this 2.5 hour run. We also conducted the same study at heavy load, 2 to 3 times a typical sector load that we experience today. Of course, as you will notice, the number of conflicts, the number of instructions are all larger, clearly, because it's a much heavier load. But we didn't lose in terms of track miles, we didn't lose in terms of efficiency. But of course, the magnitude of some of the clearances were larger than under normal load. With this, I will take a pause to sort of see if there are any questions. There is a very illustrative video and multiple scenarios that are there, and there is a pointer to the same at the end of this particular talk, which is covering 3 scenarios. One very simple scenario where an increase in ground speed action between the 2 aircraft circled, in yellow, orange, or brown color they have a possible conflict in the future as shown in the figure, and how an increase in airspeed is recommended to sort of mitigate the specific action. And more complex actions, as we see, it's a 3-way conflict between the 3 aircrafts highlighted in circles, and how we are issuing separate clearances to 2 of the aircraft so that this particular conflict can be avoided. And more examples where a particular aircraft fails to follow a clearance or imperfectly follows the clearance. The clearance was for 5 degrees, but the pilot only turned by 2 degrees, and really the follow-up action gets taken subsequently. Here is a link from LFV, which has a YouTube video explaining these scenarios in more detail, but I'll pause here to see if there are any questions.
Do you also want a discussion now? Is the video optional, Mudakar? If there are no questions, we get a video, or is there more to come? And because if we want to discuss your work, do you want it later, or can it also be asked now?
Now, please. I think I am at the end of my charts. Okay. I thought I'll pause here. Good, if needed, we can go over some of the videos for the live video demonstration, but otherwise, I'm happy to take questions.
Fine, then I fully understand. So if there are any questions, please use the Q&A button underneath. You can press and then select any questions. Currently, there are no questions. I'll kick off the discussion. Maybe this inspires some more questions. I have 2 questions, actually, Mudakar, that you could perhaps address. One for clarification and one to yeah, maybe deliberate a bit on the comparison. So, but first of all, is if you go in your slide 19, there is the explanation of the action space. And I also wondered this when I read your paper. You say that there's the action spaces to have a change in ground speed, change in heading or azimuth, or change in vertical speed, altitude, basically.
Right.
And this, of course, gives the option, and you show in the figure three options. You see 001, 010, and 100 as each of the dimensions where you can do a change.
Right.
In your paper, you say, but there you talk about the combinations.
Yes.
Positive and negative, and then you say, well, there's positive, negative for each of the dimensions. There are 3 dimensions, so that gives us an exercise of 8 options. Correct. So we have 3 on the slide, 8 on your paper, but then you later say, but there's also the option of doing nothing, as we see on the slide, which means the dimension is actually from -1 to +1. It gives 3 quanta basically per step, and then the action space would be 3 to the power 3, being 27. So I was wondering, what is the action space that's being used? Is it 3, 8, or 27?
None of the above. Sorry. Let me explain that. The answer is none of the above, but let me explain why that is the case. Right. So in every dimension, we can define what is the minimum quanta. So for example, in the ground speed dimension, the minimum quanta is 0.01 Mach, but I can go up to 5 units of quanta as far as this figure is saying. But in reality, we go up to 10 units of quanta. So it all changes from plus 0.01 Mach up to 0.09 Mach, and all the way from minus 0.09 Mach all the way to plus 0.09 Mach, for example. Those are all the units of change that are permissible, right? So if I say, if I have 10 possible or 20 possible choices to make here, or let's be very precise, from minus 0.09 Mach to plus 0.09 Mach, I have, let's see how many quantas are there. 9 plus 9 plus 1, 19 possible quantas are there on the change to the ground speed domain. Similarly, for azimuth, again, we can go, let's say, from minus 30 degrees to plus 30 degrees at a quanta of 5 degrees. So then you have.
So you do more, for each action, you also consider more quantas in one step, right? More quanta in one step.
So what you see as 001 here, 1 refers to the number of units of quanta that we are changing. Okay. I just, let's for now, let's for now forget the negative numbers just to make the explanation easy. Let's only look at positive changes to ground speed, azimuth, and altitude. Again, just to keep the discussion simple. So you can think of 533 as changing the ground speed by plus 0.05 Mach. And azimuth by 15 degrees and altitude by 3,000 feet, right? But there are many.
Sorry to interrupt you. I mean, sure. The point of the different quanta is clear, but it is exactly about the sign that my question is actually. So yes. We could make the discussion simple by going only in the positive direction. But my key question is, how do you decide between positive and negative?
So the lattice space that we are building covers both positive and negative. Okay. Now, we are simultaneously exploring plus 1,000 feet and minus 1,000 feet altitude change, for example, and wherever we are. So if you think of 001, it implicitly has 2 actions in it, which is plus 1,000 feet and minus 1,000 feet. Maybe a more interesting example is 011, for example, which implicitly has 4 actions, plus 5 degree, minus 5 degree, plus 1,000 feet, minus 1,000 feet. 2 cross 2 combination gives you 4 options.
I see. Okay, so it's every time when we see 1, actually it checks for both directions, plus and minus 1.
And in most cases, when there is, see, if there is 0, plus 0 minus 0 is 0, so it doesn't make any change. But anytime we are talking about 433, 533, all non-zero, there are actually 8 implicit actions there. Because in each of the dimensions can be plus 4, minus 4, plus 3, minus 3, plus 3, minus 3. So the combination is 8.
Okay, okay.
Yeah.
Thank you.
So those are the actions that are explored today. And the key to the action exploration are these rules, because if I assume, if I have 19 possible choices for ground speed, because I'm going from minus 0.09 Mach to plus 0.09 with a quanta of 0.01. So it's 19 multiplied by whatever. If I have 10 choices for azimuth, 10 choices for altitude, 19 times 10 times 10. In reality, we have an action space that's of size roughly 8,000. So there are 8,000 possible, there are 1,000 lattice nodes, and on an average, each node corresponds to 8 possible actions because of the plus and the minus. So that's the state space that we are exploring. It's a very large state space to explore. Hence, we have these lattice pruning strategies. This is a classical AI search space problem. So if we say that a particular action succeeds, say 001 succeeds, we can prune the entire lattice that dominates 001, and that is how we get immense speed up and scale out in the process.
Okay, yeah, I think, yeah, so once you have encoded it like this, I think we understand how it works, but it was just this encoding that we were wondering. There is a question by somebody who was also presenter in this, was a presenter in this room before, so his question appears in the chat and not in the questions, but I can read it. You can also read it. I can read it out loud for the audience. It's Ramon Damo who asks, I may have missed something, but is the action selected based on individual rewards, or is the joint action selected for the whole set of flights, taking into account a sort of community team rewards? Okay,
so currently the actions are taken based on the goal of avoiding separation loss. Separation loss by definition is a sort of a community reward. It's not just based on one aircraft. Separation loss is always between two or more aircrafts. But there is no joint reward that we are having on the late arrival of an aircraft, and those additional objectives we are not considering. The only joint objective we are considering is safety across multiple aircrafts, because once we decide that these three actions are safe, the choice of the optimal action is being done just based on the affected aircraft alone, not based on jointly across multiple aircrafts. So yes, those are some of the future work items that we have in the pipeline. But you are right, currently the only joint objective is separation loss.
Yeah, it's an individual reward, but because the conflict is with another aircraft, it's a reward for two aircraft in the end, right?
Yes, I mean, it can be more like, for example, if I go to this particular scenario, there are three aircrafts that are, in a sort of a conflict. So here you will see that there is 915 aircraft coming from the south, 900 coming from the north, and 911 coming from the east. So the three dots that you see are giving you a indication of the direction in which the aircrafts are coming from. So the planner is determining a loss of separation 10 minutes in advance in this particular case, right? And then the action that we are recommending is for multiple aircrafts so that jointly they can avoid all the pairwise separation losses. Yes,
of course. So, yeah, I see. And Ramon also says in the chat, thank you, very clear, and comments you for your work. Nice work, he says.
Oh, thank you.
There's also a question from Miroslav. Does the model take into account the airspace and weather conditions too?
So currently, those are things we are not taking into explicit account here. No-fly zones, wind speed, weather conditions, we are not taking into account. But if weather were just a geopolygon and an altitude range that we want to avoid, like for example, you could draw a geographical polygon and say avoid that polygon from 20,000 feet to 30,000 feet. That is something that can be factored rather easily into the AI planner. The more complicated things are wind speed, because wind speed can be different at different altitudes. Today, we do not have explicit information about this wind speed information. Factoring that into the projected future state of an aircraft. Because today we are simply doing projectile motion. We are sort of extrapolating on the elliptic arc on which the aircraft is traveling towards the next waypoint, or a linear ascent or descent in the altitude dimension. That's what is modeled. But of course, some of these things could get affected because of wind speed considerations. Those are not handled by the model. But having said that, we are doing continuous planning. So while I may expect the aircraft to be at a particular lat-lon at a particular altitude 20 minutes from now, it can get revised 10 minutes from now or 15 minutes from now, because for whatever reasons there could be headwind unaccounted for by the model, which could have altered the position of the aircraft. So continuous planning is a weak compensation for not truly accounting for weather related challenges. But we do plan to incorporate things like wind speed, which will directly impact the ground speed of the aircraft in the near future.
And this continuous planning works really well in simulations, of course, but in reality, there is a limit to the amount of updates you might want to receive. The frequency shouldn't be too high, but one iteration when it gets closer is something that might typically, when you cross a certain threshold value. Another way might be perhaps to include some uncertainties, right? Because some of those things are really small deviations from what you expected, and maybe slightly larger margins between the what your action is and what you detect might already solve some of these issues.
Yes, spot on. I think we do account for uncertainties in this model here. The way we account for uncertainty is that we are continuously estimating the mean, the expected position, with a small variance around that mean, where the aircraft might be in the future. But there are, I have three things in my head right away in terms of what we were planning to do in terms of improving the uncertainty handling. For a variety of reasons, there are some interesting corner cases that again need to be more closely examined. These are things that happen when I know a conflict is going to occur, but the aircraft is outside the sector. But if I wait for the aircraft to enter the sector, I have very little time to make changes. So we do go make a change on the aircraft within our sector, even though that may be the less efficient thing to do. So we do account for those timing related uncertainties to a certain degree. But I would say there is a lot more to be done to more holistically account for uncertainty.
Yeah, thank you. Well done so far. Room for improvements is what Miroslav reacted to your answer. Thank you very much. Yeah, in general, I think it's also a very common practice, right, to take slightly larger margins for your conflict resolution actions, therefore your detection, to have to avoid high frequency reactions. Indeed.
Exactly. We do that, and we also, by forecasting ahead with the additional uncertainty buffer, we do make sure that we do not do knee-jerk actions, because we do rate limit how many actions we can relay as an explicit parameter inside our optimization formulation, right?
Yeah. We have one final question, because looking at the time, we have to also prepare for the next presentation, but there's one final question in the Q&A by Olivia Nunes. In your simulation run, did aircraft climb and descend as per their flight plan without an explicit clearance, or would the controller give a clearance for climb descent? If the former, did the system know what the vertical profile was, or was it unknown?
So in this case, the planner is identifying what should be the change in altitude if we are trying to avoid a conflict. But the flight plans do include waypoints and anticipated cruising altitudes between those waypoints. So there is a flight plan which covers that information. But when it resulting in a conflict, the AI planner is recommending a new altitude for that aircraft. We also do attempt to bring the flight back to the original altitude once the conflict goes away. Much like when we suggest an azimuth action, we change the heading by 5 degrees. We have to bring the flight back to the flight plan. Yeah.
Okay, thank you very much. I had more questions and more things that we could discuss, I think, but this is we have to do offline maybe on another occasion. For now, thank you very much, Mudakar, for this interesting presentation. Generated quite some discussion. Could you also share the link of the video, perhaps in the chat, so that people want to check out this video later, that they can do so by clicking on the chat. So, right away. And then share it with everyone, so to everyone in the chat, so that everybody can click this. That would be nice, perhaps.
Done. So you should have it.
Yes, we do. Thank you very much.
Primary language is Swedish, but there is an English translation. The video is, of course, with the English narration. So
okay, for me as a Dutchman, the Swedish will probably do nicely.
Of course, of course.
Okay, but for the others, please use the English subtitles. And thank you very much, Mudaka.
Most welcome. Thank you.
So we're just in time for the next presentation. The next presentation is by Ralfi Isufaj. I hope I pronounced it correctly, Ralfi, but if so, please correct me if I'm wrong. He's from the Autonomous University of Barcelona. I think every university wants to be autonomous, right? So the Autonomous University of Barcelona in Sabadell, Spain, probably suburbs of Barcelona, Sabadell. He received his bachelor's degrees in computer engineering at the Polytechnic University of Tirana in Albania in 2014, and his master's degree in 2018 in computer science with a specialization in artificial intelligence at the University of Freiburg in Germany. Since 2019, he's pursuing a PhD degree with the Department of Telecommunication and System Engineering in the Autonomous University of Barcelona, and his research line is on machine learning applications to air conflict resolution. So if you could share your screen, Ralfi, then we can... Yes, we can see it and unmute your mic. Yes, you're all set. Good luck.
All right. So, hello everyone, and welcome to my presentation. In my talk about my paper that I worked with my colleague and my supervisor, Michael. Okay. So my talk will be structured like this. I'll first introduce the work and try to motivate why we're trying to do what we're doing. Then I'll talk about some theoretical background, that is stuff that you kind of need to know to understand what we're doing here. And then I'll talk about how we sort of model conflict resolution as a multi-agent reinforcement learning problem. And then I'm going to present some results and sort of draw conclusions and talk about what we can do next. Right, so basically for this paper, we're in the context of conflict resolution for ATM at the tactical phase. At the tactical phase, so safety is guaranteed through minimum pairwise separation, which is 5 nautical miles horizontally and 1,000 feet vertically. At the tactical level and route, safety is guaranteed by human controllers. And as our field is going more and more towards sort of automation and sort of decision support tools for controllers, these tools are sort of the pillar of automation, and that's what we're trying to build on. Right, so but basically there exists plenty of conflict resolution algorithms, and do we even need an extra one to add more confusion to things? But the problem is that a lot of these algorithms, or the majority of algorithms, don't consider other factors except for sort of the fact that they solve the conflict or don't solve the conflict. So they don't really try to bother to see if they're sort of causing other conflicts or making the airspace more complex, or how much extra fuel they're sort of spending and so on. And furthermore, they also, a lot of them make limited assumptions about airspace. So first of all, the majority of them discretize this airspace, and that can lead to some shortcomings when tested on real traffic. Why are we choosing to use reinforcement learning? Is because so we want to see if we don't give any sort of bias, if we don't introduce any sort of bias to the solver, what kind of solutions do we get? And let's say we're using some sort of supervised learning, for example, we would have to imitate other solutions, and this is not what we're trying to do here. And sort of the main objective of the paper is that we're trying to improve or tackle the not just the conflict resolution by itself, but also sort of the quality of conflict resolutions based on sort of combining multiple factors. So as we said, I'm going to use reinforcement learning. We're using reinforcement learning for our work, which is a paradigm of machine learning that's where sort of you have an agent that can be a piece of software or a robot or something is interacting with an environment, and as a result, it takes actions in this environment and gets a reward. And the goal of this agent will be to sort of maximize the reward. So, and this is how it learns, it sort of tries to improve its reward through interacting with the environment. And the way that a reinforcement learning problem is formalized is through a Markov decision process, where we have, like I said, we need to talk, but we need to have an action space and a state space. We need to sort of formalize the reward and a transition function in case where's the model, or if there's no model, no transition function. Yeah, so basically through solving the NDP, we're solving the reinforcement learning problem. But in our work, we are using multi-agent reinforcement learning, and the problem there sort of explodes in difficulty a little bit, because sort of the more agents you consider, then the more interactions you will have, and you add non-stationarity to the environment, because the one agent will observe part of the other agents as part of the environment, and you will have an ever-changing environment. And this is sort of formalized by extending a Markov decision process to a Markov decision, to a Markov game, where each agent sort of has its own behavior, and it's trying to maximize its own reward, depending on the behavior, on the sort of the behavior of the community, if it's a cooperative reward or it's a competitive reward, and so on and so forth. And obviously, the more agents so in the case where you have multiple agents, the individual reward is obviously a function of all policies. So the actions of another agent can sort of affect the first agent, and so on and so forth. So there's plenty of ways one can try to use to solve the MDP, the Markov decision process. But in this work, we focus on a group of algorithms that are methods that are the deterministic policy gradient methods. The characteristic of these methods is that they try to optimize the policy. So the policy is sort of it's the agent's strategy to take an action in a certain state. So other algorithms try to sort of improve the reward, to optimize the reward, to get the most reward, but policy gradient methods sort of try to improve the action itself. Most policy gradient algorithms are implemented as an actor-critic model, which means that there are two modules, an actor module and a critic module. The actor sort of is the one who's learning the actions, who's trying to say, okay, this is the action we should take, and it improves on the policy. And the critic, which tries to sort of approximate the value function. And basically, you will have practically, it's in the name, so the actor takes an action and the critic says, okay, I think you did good, or I think you did bad. These sort of models make it possible to have continuous action spaces. So in other sort of models where you only optimize the value function, it would be impossible to have to sort of optimize each action, because it would be impossible to sort of iterate over them. And with this group of methods, this becomes possible. And as is usual in other sort of reinforcement learning algorithms that sort of use neural networks to approximate as function approximators, there's target networks that are needed. So both the actor and the critic is usually implemented as a neural network. And for each, the actor and the critic, a target network is needed. So a target actor and a target critic is needed to make to stabilize learning. So I'm going to talk now how we sort of, so knowing all this, I'm going to talk now how we formalized conflict resolution as a multi-agent reinforcement learning. So in order to do that, we need to formalize the Markov decision process, or the Markov game. Now that we're talking for in a multi-agent setting, for that we need to define or formalize an action space, a state space, a reward function, and we also need to know when do we stop the model, and we also need to decide if we give the agents perfect knowledge, or we only give them imperfect knowledge. Basically, we may make them partially observable. We need a learning algorithm. So how are the agents going to learn? How they're going to improve on their policies? And in this work, we use multi-agent deep deterministic policy gradient. It's a bit of a mouthful, but MADDBG basically. And I'm going to talk about it later. And we also need scenarios. So we need to train the model on some scenarios and sort of try to see if we can generalize. So let's go at them one by one. So first of all, I'm going to talk about how we formalize the action space. And as I said a bit earlier, using deterministic policy gradient method allows for continuous action spaces. In this work, we sort of chose to only work on to solve conflicts on the horizontal plane, and we cap the heading changes that an aircraft can make per time step at 45 degrees at either direction. And a speed change. So we assume en route traffic, and en route traffic we assume aircraft to fly at optimal speeds. So we allow aircraft to make a deceleration of at most 6% and an acceleration of at most 3%. Then the output is given as a sinus and cosinus of the heading change and the percentage of the speed change. So the reason that we and then the sort of the angle is basically the inverse tangent of the sine of the angle. So sinus over cosinus. So the reason why we do this is because we observed in earlier sort of runs or experiments that the network was saturating at the highest value. So we would always get a heading change of 45 degrees either direction, even if it was not needed. So this was sort of a numerical trick that we employed to overcome this issue. Furthermore, as is customary in reinforcement learning problems, we add noise to the actions to sort of ensure exploration. So in reinforcement learning, exploration versus exploitation is a common issue that an agent will sometimes plateau and think that it's doing great, but there's a better action that you can take, and this is sort of ensured by adding noise to the actions. And for this work, we found that simple Gaussian noise worked good enough. Now for the state space, we chose to keep it relatively simple. So the state of each of an aircraft, of an agent, is basically represented by its position, so latitude, longitude, and as we said, as we only consider horizontal solutions, we don't consider altitude, its heading, and its speed. So basically, yeah, and this is the sort of the states that we decide. Furthermore, we also make the Markov decision process, or the Markov game, partially observable, and therefore the aircraft can only have information about its five closest aircraft, including itself. Right, an interesting thing, which is basically the main motivation of our work, is sort of affected by the rewards function. So the behavior of the agents in reinforcement learning is affected a lot by the reward function. And like I said, in this work, we don't only want to solve conflicts, but we also sort of want to tackle the quality of the solutions. And the factors that we include in our reward function is time until loss of separation and the closest point of approach. So the motivation of this factor was that if you have a conflict that is happening, so basically the more you take to solve the conflict, the more you're sort of penalized for not solving the conflict in time. And the other factor that we also consider the CPA is that we consider different geometries of conflicts. And practically, if you have a head-on collision, then we need to sort of make a bigger, need to make a bigger heading change. And for example, if you have two aircraft that are in parallel, or almost in parallel, and will be a little bit in conflict at some point. Something else that we consider is the difference from track and optimal speed. So we discourage the agents from making big heading changes. So smaller heading changes and smaller speeds, changes in speed are sort of encouraged. We also consider fuel consumption. which we sort of modeled from this OpenAP framework done from the people in TU Delft. And yeah, basically it goes in line with the difference from track and optimal speed, that we don't want the solutions to be super inefficient. So we only we want to encourage solutions that don't sort of cause the aircraft to spend a lot of fuel. And the last two sort of factors are about sort of the complexity of the airspace. So first of all, the agents are heavily penalized if they make if the solution of the conflict creates a new conflict. This is not something that, for example, controllers do, and this is not something that we wanted our models to do. So they're heavily penalized. And lastly, we also consider airspace complexity, which sort of is we formalize by using aerial ecosystems, which is a hierarchical structure that considers all the aircraft that would be affected by a solution. And practically the aircraft that are in conflict are the first order of the ecosystem, and down the line with more and more aircraft affected. And practically what we see is that if an action, or if a proposed action or a solution from the model creates a more complex system than it previously was before the action was taken, then we sort of penalize this action and we don't allow it. And it's worth mentioning that all of these rewards are negative. So basically it's a cost function. So we sort of penalize the reward. So it's negative reinforcement versus positive reinforcement, and we penalize the agents for taking a wrong action. And finally, the end result of the reward is a weighted linear combination of all these factors. And now, yeah, another important part is the learning algorithm, as I mentioned. And in this work, we're using MAD-DPG. It is a generalization to multi-agent system of deep deterministic policy gradients, and it has the principle that it works on is centralized training, decentralized execution, which means that for each agent you have an actor, but you have a centralized critic. This means that the critic has access to the observations of all agents, or has access to the policies of agents, but other agents don't sort of interact with each other and don't know the policies of the other agent. They sort of only observe the other agent as part of the environment. So practically what happens, how the algorithm works is that you start a scenario, which is these 5 aircraft and the time t. From that scenario, we extract the state representation, which was this latitude, longitude, heading, and speed. And basically, we form a matrix of 5 by 4 in our case. These observations then are fed to the model, which is the centralized critic and the decentralized actors. And the actors then propose an action. And the action is taken by the agents. And then we observe a new state in the environment. And then we also observe a reward, which is passed back to the critic. Then the critic sort of tries to minimize its prediction, the difference between its prediction and the actual reward. And then using this prediction, then the actors are sort of also updated to minimize the difference. And lastly, what we needed to sort of formalize the conflict resolution as a multi-agent reinforcement learning problem are the scenarios and where we simulate our stuff. So basically, we consider pairwise conflicts only, and the data is real data from DDR2. An episode lasted 20 minutes, and the conflict starts between 0 and 5 minutes from T0. We consider surrounding traffic, as we said, by considering these by forming an aerial ecosystem, which, like I said, determines which other aircraft would be affected by the solution. Agents take an action every 15 seconds, so it's continuous decision making, which might be a bit off-putting because this is not how usually conflicts are solved. So conflicts are usually solved, just take one action and it's properly solved. But the problem was with the data was we didn't have a lot of sort of geometries, a lot of scenarios, so we feared of lacking in generalization power by just training in the sort of scenarios that we had. So we employed a simple data augmentation technique where we take a scenario. So for each scenario that we have, we take the scenario, we remove one of the conflicting aircraft, and then we add another aircraft depending on a random sort of intrusion angle. So for this, so basically we sort of multiply the amount of scenarios we have using this technique. And from that, we had, in the end, we had around 1,000 training examples where we trained the model on, and 195 test scenarios where we sort of evaluated the performance on unseen scenarios. So the simulation environment was the Blue Sky simulator, which is an open source ATM simulator. And the model was trained for 2,050 episodes. So, I mean, there's 1,000 training examples, 2,050 episodes, which basically means that the model is trained multiple times on the same scenario. Training was done on a Google Cloud platform using a GPU, and training a model. So the model that our best performing model was trained for around a day and a half or so. All right, now that we have all this behind us, so we basically have modeled this problem as a multi-agent reinforcement learning problems. We have pairwise conflicts, and we're trying to solve pairwise conflicts by making a heading change and a speed change at the same time. Now let's see how our model sort of performs. Like I said previously, we tested on 195 scenarios. 93% of these conflicts were solved, which is a relatively good result, and it's made better by the fact that no new conflicts were created. But nevertheless, we think that just looking at the amount of conflicts solved is not really informative. So it would be a bit more interesting to sort of see different aspects of the resolution. So the first thing that we can look at is the number of time steps needed to solve a conflict. So if you remember, the agents could make a decision every 15 seconds. A decision, of course, was a combination of heading speed and heading change and speed change. Nevertheless, we can see that around more than 60% of the scenarios were solved in only one time step. This is a promising result because it shows that even if we don't give the model any sort of knowledge of the environment or the dynamics of the environment, it still manages to learn some sort of desirable behavior that resemble a natural solution. So basically, like I said, controllers tend to solve these conflicts in one go, and we can manage to do the same in around 60% of the scenarios with our model. In any case, around 90% of the scenarios need 5 time steps or less, which is still a good thing, because in any case, we can see that our model can solve the majority of conflicts in around a minute or so. However, there's still some sort of edge cases, or some, however you want to call them, that take more than time steps to be solved, and we will look at them a bit more here, where we sort of see the relation between the time to loss of separation and the time the model needed to solve the conflict. And from what we can see here is basically that the majority of times that the model sort of couldn't solve a conflict or solve the conflict with a lot of effort was the times that the conflict, sort of the model was called as the conflict was started. Now, so we don't envision our model to be used in this sort of scenarios, because that would be a job for TCAS, let's say, or something like that. But this would be sort of, we wanted to try to stress the model to sort of see that if it doesn't have any time to solve, what happens. And to us, it was a bit surprising, because so intuitively we thought that what would happen when the conflict had started is that the agents would make a big heading change and sort of compensate for the penalization in heading change and fuel consumption by solving the conflict. But this was not the case, and we sort of looked deeper into it by sort of simulating, creating 15 simulations of scenarios where the conflict had started at time 0, and it solved none of these. And what was happening was that there was sort of the penalization that of the conflict that started, the conflict that started. It was practically too big, and it was, let's say, confusing to the agents, and the agents couldn't get sort of around it by it never sort of learned to get around it by making bigger heading changes. And that's practically a testament to sort of how important is this sort of the proper formalization or proper calibration of the reward function. Another interesting thing that we wanted to look at is the displacement from the original track. So basically, how far were the aircraft from the original track when the conflict was solved? And from what we can see is that the majority of conflicts are solved with the aircraft moving less than half a nautical mile from the original track. And this is sort of I think this sort of speaks to the importance of the reward function, because the models tend not to take big heading changes, as we'll see a bit later. They don't tend to take big heading changes, and don't tend to sort of, which can, I don't know, which obviously can cause delays and more fuel consumption and so on. And they prefer sort of smaller heading changes to solve the conflict. Now, this is, I think this is very interesting, because we're looking at sort of the average heading change and speed change per test scenario that from the 93% of conflicts that we solved. And as we can see here on the top figure, agent 1 and agent 2 don't usually take big heading changes. So we have agent 1 taking a relative taking a heading change of 20 degrees. So in this case, we don't really consider if it's 20 degrees this side or that side. It's basically the magnitude of the heading change. And agent 2 makes an average heading change of around 30 degrees. And like I said, this practically shows the agents are able to sort of learn somehow desirable behavior by not having any sort of context before giving to them. And an interesting thing here is also the speed change. Speed change are usually not considered a very efficient way of solving conflict, and they don't solve all conflicts. For example, consider sort of a head-on case or a near head-on case. Speed change wouldn't be able to solve that. And from what we can see is that the model doesn't prefer the agents don't prefer at all to solve conflicts by doing any heading changes.
Ravi, where are we in terms of, so how many more slides do you want to discuss, because we're running fast in time?
Yeah, I'll pick it up. I'll pick up the speed.
Yeah, so we have some time, because there are already some questions. It would be nice to have some time for the discussion.
Yeah, I'll be faster. Sorry. So basically, in the end, we're showing the correlation between the final reward and time step. Basically, what we can see is that the quicker the model is solving the conflict, the less it's penalized, and it sort of makes sense, because it will stop getting penalizations. And even though this is we don't really expect the agents to have a linear in the end, because the value function is learned through the critic. We don't expect them to have a linear sort of correlation between all factors and the final reward. But still, it's nice to see that the faster it ends, the quicker, the less it's penalized. Nevertheless, it's not all good. We had some strange results where sort of here we have 5 different cases, and we sort of see the heading change in the direction, and we can see that in some cases both agents made a heading change in the same direction, and it's not really something intuitive. That's something we're trying to work on. So to conclude, in this work we have modeled pairwise conflicts as multi-agent reinforcement learning. Like we said, in addition to solve the conflicts. We create a reward function that attempts to tackle the quality of solutions in terms of airspace complexity and fuel consumption and so on. We trained and tested on real traffic with data augmentation, and we achieved a success rate of 93%. And we show that even without prior knowledge, the agents can learn some desirable behaviors. But nevertheless, there's things to improve. First of all, we have to improve counterintuitive behavior. That is the cases where the agents sort of made the heading change in the same direction. In this work, we sort of consider cooperative agents, which might not always be the case. So it would be interesting to investigate competitive or mixed agents. In this case, we believe that one way to sort of improve the acceptability of the resolutions would be to expose the models to expert knowledge, or let's say to either through a better calibrated reward, or let's say through a teacher where whenever an action is taken, except besides the reward, you also have an outer signal from a human, let's say, who says it is good or bad. We also want to work on, we're working on at the moment on graph neural networks, which is sort of which we sort of believe will improve sort of the way the agents cooperate or interact with each other through the sort of inherent communication that graphs have. And furthermore, and lastly, explainability is also an important factor in our work, and which we want to explore. And basically, we want to explore how to sort of what are good explanations and how to sort of present these to humans. Yeah, it's acknowledged to Cesar Giu, who is funding my PhD, and this is all from my side. Thank you. Sorry if I took long.
No, we still have some time for the discussion. Thanks, Ralphie, for this presentation. There are a number of questions. I see two very similar questions, one in the chat and one in the Q&A. The short version of the question by Nicolas Durand is: 2 aircraft conflicts are easy to solve. How can you generalize your approach to more than 2 aircraft scenario? Do you think that it's possible? And I think the same question is actually asked by Ramon Dammo in the Q&A, or a variation of it. At least he says that the multi-agent deep deterministic policy gradient method works for a finite number of agents. So if you train the policy with n agents, it will work with n agents, and is your n always 2?
Right. For this work, the n is always 2. And there were sort of considered other scenarios where we'd have more than 2, but we would solve the conflict by moving 2, for example, and the other would remain in the same. But we thought this was outside of the scope of this work, but this is what we're working on graph neural networks, and the preliminary results show that it makes it easier to train teams with a bigger number of agents through that than through MADDPG, and we think that's because of the sort of the non-stationarity on the environment, and giving the agents the ability to sort of observe each other's observations. We see that it makes it a bit easier to train teams with more than 2 models.
Yeah, but
2
is
agents.
it possible to increase the number of?
Yeah, yes, we believe so. We believe so. Yes.
So it's still to be done. It's on the wish list.
Yeah, we're working at the moment to have more than 2 aircraft.
Good. And the other question in the chat is: have you considered the same state action reward definition with another algorithm, such as MACC, G2? ANet to account for moving communities? No, we only have sort of considered this multi-agent algorithm. We tried various sort of single agent algorithms to sort of make it work in a team, but their results were not really that good and didn't compare to the performance of MADDPG, but we didn't try any other multi-agent algorithms. Okay. And there's a question in the Q&A that says, were the conflict resolutions the same or similar to what a controller would issue as a resolution? Were you able to have a controller look at the solutions to compare with what's normally done? Because one of the reasons, your motivations you mentioned, is to also look at original solutions that could come up.
Well, yeah, I mean, we haven't been able to really get in touch with any controllers to sort of have them evaluate the model. But in any case, this was the point of this work wasn't that. We're not trying to sort of represent, we're not saying that we present the final work in a sense that it's ready to be validated by people. We're saying that we don't give the agents any sort of prior knowledge. They don't know what's up and down, what's left and right. And we wanted to see if we sort of can achieve any desirable strategies. For example, the thing that the result that they don't prefer to change the speed at all is sort of to us makes sense to say that it is a desirable strategy that is learned, where you prefer to sort of move around the aircraft and not really, because we saw cases where we had a head-on case and the speed change was 0. In those cases it was 0 and it only moved the heading. So for example, cases like this, where the fact that the majority are solved through in only one time step is sort of let's say proof or confirmation that the models can learn desirable strategies.
Yeah, and I think so. So we also looked at machine learning for similar reasons, to come up with completely blank slate. Start with a blank slate and then see what kind of new tactics would evolve. Because also you mentioned the explainability of these kind of algorithms is hard, but those tactics may be recognizable and then could be implemented in a system that is used in practice by adopting these policies maybe, or the things, the tactics, the strategies that you discovered in this way. Would that be an application of this work?
Of course. But to me, the point of explainability is, well, we want to explain it to people. And it's to me, it's better to figure out what is a good explanation. So have people to say that this is a desirable explanation, this is a complete explanation, rather than just, let's say, wanting to know the inner workings of a neural network, because that's not really useful for the controller. For example, the controller would be more interested to know why this action was taken and be satisfied with this answer, or the counterfactual example, why this action was not taken, and be satisfied with that example.
Yeah. To use it as a generator for strategies and then implement the strategies in the operational system. Something.
Yeah.
Yeah. Okay. If there are no more questions, then looking. So please don't hesitate to put the Q&A or in the chat. I do have one more question myself. Do we still have time? We have 2 minutes left before the next presenter.
Let's go.
If nobody wants us 2 minutes, then I have one more question. So you say at some point you say one of the rewards that elements of your reward function was that no new conflicts are created.
Yeah.
But this also has to do with multi-aircraft conflicts, perhaps. But sometimes it's not a bad idea to have a new conflict created, because in the long run, it is still the optimal solution. That you consider that that option, that sometimes if you have really complex configurations, that maybe triggering a conflict is not the worst thing in the world.
Well, I mean, when you say optimality, you sort of have to prove optimality, and you can't just assume optimality and go, okay, we say, okay, this is optimal. But obviously, if you consider denser sort of airspaces, then I think having an algorithm that only considers pairwise conflict is not enough, because the probability of that you will have a higher probability you'll have a conflict with more than 2 is much higher. For example, if you take the example of drones, this is one way that they sort of define the capacity of the airspace. So if you have if you have a certain airspace with a certain amount of drones in it, if the probability that it will have a conflict with more than 2 aircraft is higher than a threshold, that's the capacity of
no, but also secondary conflicts. So initially it might be one-on-one, but it might be that as a result you get further ahead, perhaps trigger new conflict, but because it's further ahead, you still have improved the situation. And then it might still be the best way out. Yeah. Obviously.
And like I said, in those cases, it might be better to create a new conflict, but we don't really know. We would have to sort of see if that is the case. And in this work, we don't really consider the airspaces that are that dense. It's mostly to have this from, like you said, from this blank state, how good we can get. But in my sort of assessment, we would need an algorithm that sort of learns with more, that tries to solve conflicts with more than 2 aircraft.
Yeah, that would certainly be interesting. So looking forward to those results, because you said we're already working on that.
Yeah,
so,
me too, actually.
Yeah, okay. Well, we're looking forward, I think, all of us into the next part then of the part 2 of this work. Thank you very much, Ralphie, at least for your presentation, your clear explanation of your work. So we are just on time, I think, for the third presentation of this session. And that's by Sarah de Gook. I hope I pronounced it correctly.
Yes.
Sarah de Gook is a master's student in operational research from ENAC, École Nationale d'Aviation Civile in Toulouse. And yes, he has also a paper on applying artificial intelligence algorithms and conflict resolution, but in a rather original way, I think. So the title of her work is Learning Uncertainty Parameters for Tactical Conflict Resolution. She has already shared her screen, so I'd like to give the floor to Sarah. Good luck.
Hello, everyone. I'm going to present a research entitled Learning Uncertainty Parameters for Tactical Conflict Resolution, carried out by researchers from the ENAC Optimization Lab. First, I will introduce the subject and the context. We will then explain our model and the method used to answer our problem. The next step will be to validate the models developed on artificially created data. Thus, once we have verified that the model used worked correctly on this data, we will be able to apply and calibrate this model on operational data from experiments. After all this, we will conclude on the different results obtained. One of the objectives currently targeted in air traffic management is to allow air traffic controllers to manage traffic in the context of less structured routes with a high demand. Current research focuses on developing decision support tools that should help reduce the workload of air traffic controllers while improving the flow of traffic. However, very few assistance tools are offered and adapted to air traffic controllers. One of the major problems we have is the lack of precision on the trajectory prediction due to uncertainties related to the climate conditions, the lack of precision of radar surveillance tools, pilot reaction times, and other factors. The first objective will then be to set up an uncertainty model linked to the behavior of air traffic controllers during conflict resolution. Then it will be necessary to calibrate these uncertainty parameters on situations solved manually. So I will now summarize in a few items the context of our study. Our problem focuses on real-time en route air traffic control, which consists of surveillance, coordination of adjacent centers, and conflict resolution by different simple maneuvers, heading change, flight level change, speed modification, transmitted to the pilots. Air traffic controllers are trained to conflict detection using a 2D horizontal visualization of traffic. Controllers can measure distances between points, but this information is not automatically displayed on the screen. The third dimension is managed by a label that displays the altitude and attitude of the aircraft. Data was collected using a field survey performed in 2 en route air traffic control centers. The results showed that controllers, in addition to reducing and recognizing uncertainty, can deliberately increase uncertainty in order to increase the flexibility of the other actors in the system to achieve their operational goals. In trajectory prediction, some uncertainties are constant, like the speed, and others increase with time, like the future positions of the aircraft. Several approaches have already been discussed in previous work. Among the interactive detection tools, we can notice the highly interactive problem solver (HIPS) approach that was issued from ARC 2000. It is a geometric approach considering uncertainty on speed. The main problem of this approach is that it doesn't manage heading changes nor returns. On the US side, many other approaches were issued from Esberger research with a probabilistic model that was then used by many other projects. He proposes to predict the probability that the separation between two aircraft falls below a certain separation threshold. This probability is called the probability of conflict. However, this method remains quite far from the vision of the controllers, and the resulting information is hard to use in operation. Finally, detecting potential conflicts without inventing them is a complicated problem that has not yet been solved. Now, let's move to the problem modeling and the choice of the learning method. Let us quickly remind the initial problem, which is to set up an uncertainty model linked to the behavior of air traffic controllers during their conflict resolution task, and to calibrate these uncertainty parameters on situations resolved manually. Some initial assumptions on simplification can be stated. First, our conflict situations are located only in 2 dimensions in the horizontal plane. Consequently, the maneuvers, which we'll subsequently define, can only be heading changes. In addition, in a scenario, the aircraft speeds are constant. When resolving a conflict, the minimum distance separating the trajectories after resolution approaches 5 nautical miles, taking into account uncertainties. Finally, a maximum of 1 maneuver per aircraft is allowed. Now let's define a maneuver. A maneuver is a heading change of alpha degrees from time t0 to time t1, as we can see in the illustration. The aircraft initially goes directly from the origin O to the destination D, but changes its heading at time t0 and returns to its original destination D at time t1. Let's also define the uncertainties that we are going to consider. First, there is the uncertainty delta t0 regarding the pilot's reaction time to initiate a maneuver. On the diagram, we see that the pilot could start the maneuver between t0 and t0 plus delta t0. Second, in the same vein, we find delta t1, which is the pilot's maximum reaction time to complete the maneuver. There is also the uncertainty regarding the angle of heading change, epsilon alpha. If a 10 degrees heading change is planned, then the possible future position of the aircraft will be between a heading change of 10 degrees minus epsilon alpha and a heading change of 10 plus epsilon alpha degrees. Finally, we found an uncertainty of speed epsilon s. If the aircraft is flying faster than expected, then it will turn at time t0 further than expected, and in the contrary, if it is flying slower than expected, it will start the maneuver closer than expected. With the air traffic control simulator CAT designed in the ENAC lab, we can create scenarios that can be solved by an automatic solver or solved by hand. But CAT also makes it possible to visualize the zones of potential conflicts between aircraft. For example, here we can see the conflict zones in red between the two present aircraft and their future position envelopes in white. The automatic solver, by considering the uncertainties, will try to make the red areas disappear. Now, let's define our problem. The goal is to calibrate the uncertainty model using trajectories resolved by air traffic controllers. In fact, operational data is final trajectories after resolution of scenarios solved by air traffic controllers. One of the principal hypotheses is that the minimum distance separating the trajectories after resolution approaches 5 nautical miles, taking into account uncertainties. Thus, we want to minimize the sum of the least squares between the distance separating the aircraft trajectory prediction by considering uncertainties d omega minus nd, which is 5 nautical miles, and this on all scenarios. In order to choose a learning method adapted to our problem, we will observe its different characteristics. Firstly, the minimization criterion is the result of simulation. There is no analytical expression. Secondly, the regularity of minimization criteria is not known. And finally, it has multimodal properties. It's why we have decided to use an evolutionary algorithm which is robust to premature convergence and more suited to multimodal characteristics. For the EA, we want to maximize a function called fitness. Given that previously we had a sum to minimize, it will end up at the denominator of the new function with a few added constants. A population element is a quartet of the 4 uncertainties and it has a fitness. The parameters of the algorithm are 20 population elements per generation and 400 generations. We mutate 30% of the population, we cross 20% of the population, and we use a sharing process during the evaluation step. These parameters were chosen empirically. Now we will see how our models return what we are looking for on operational data. The principle is as follows. We have a set of 40 scenarios to solve, and we seek a quartet of uncertainties. Using the CAT automatic solver, we solve these 40 scenarios by considering the uncertainties chosen. Thus, we get final trajectories resolved. We then apply our model to these trajectories and obtain optimized uncertainties at the end of the algorithm. The objective is to find the uncertainties chosen initially. Let us take a concrete example. We applied our model to a nominal case, and we obtained approximately the good uncertainties concerning the speed and the T0, and uncertainty related to the heading change close to that expected, since we found 5.8 degrees for 5 degrees expected. However, the uncertainty related to the end of the maneuver time isn't correctly determined. For this benchmark, the figure illustrates the minimal distances between aircraft after resolution as a function of their initial headings difference. In blue, we show the real distances between aircraft with no uncertainties, and in red, the distances when we consider the uncertainty boxes around the aircraft position. Each point represents a particular scenario that has been created and previously solved by our automatic solver. With the uncertainties found by the EA, in red, the minimum distances are close to 5 nautical miles as expected. We carried out this test on 9 sets of nominal cases with more or less extreme uncertainties. Several observations can be made after having tested scenarios with 2 and 3 aircraft. The speed, maneuver start time, and heading change uncertainties are well determined on nominal cases. The uncertainty related to the end of the maneuver time can be found. And the model error, which is the average of the absolute value of the distances between the trajectory with uncertainties on 5 nautical miles, is mostly less than 0.5 nautical miles. But one of a part of the error can be explained by the fact that the automatic solver discretizes angle by step of 5 degrees. But one can imagine that the air traffic controllers take a margin of uncertainty and the standards of separation targeted between aircraft. The idea is therefore to add ND as an uncertainty parameter of the generic algorithm, and we did it on nominal cases. The results remain similar, and the target standard is rather well determined. Now we are going to discuss the results obtained on operational data. The first experiment took place at the Air Traffic Control Center of France in France. We asked 17 air traffic controllers to solve 8 scenarios with 2 and 3 aircraft. In general, a very large model error was observed, almost 10 times higher than for nominal cases. In addition, for the 2 aircraft cases, we noticed that the uncertainty is based essentially on the maximum reaction time of the pilot to start the maneuver. Indeed, its uncertainty is 145 seconds, which is much higher than the initially upper bound, which was 60 seconds. One of the first explanations may be the fact that the CAT application wasn't properly explained to the users. For example, they almost never use the function to advance in time, and therefore they start the maneuvers very early during scenarios. The figure illustrates the distances on the scenarios as a function of the difference between the initial headings of the aircraft with the uncertainties determined by the algorithm in red and without in blue. The cloud of red points is spread around 5 nautical miles. 8 columns of points are identifiable. These are the different scenarios resolved by the controllers. We clearly see a great variability of the decisions of the various air traffic controllers to the same conflict configurations. This explains that the rather high value of the model error. It is probably necessary to collect many more scenarios for a panel of different controllers to give an interpretation of these results. This is why, after this first investigation and the writing of our article, we carried out a new experiment at the ENAC lab. 8 different air traffic control professionals solved 50 scenarios with the CAT simulator involving 2 or 3 aircraft. In this experiment, noise is added to maneuvered trajectories so that controllers don't get used to the perfect execution of the maneuvers. I will briefly present some of the results obtained considering the separation standard ND set at 5 nautical miles. In the first column, you have the participant identifiers and then the number of scenarios solved out of the 50 with 2 aircraft. Then you have the average of the minimum distances between the trajectory predictions without and with uncertainties. The following 3 columns contain the uncertainties optimized by the algorithm on speed, T0, and the heading, and finally the model error with the mean and the standard deviation of the absolute values of the G omega minus ND. It is generally observed that the average error of the model is less than 2 nautical miles, even if it remains close to. This can be explained by the noise that has been added to the maneuvered trajectories. In addition, there is a great variability of the uncertainties between air traffic controllers. On the other hand, when we analyze all the scenarios of all the participants at the same time, we obtain an average error which exceeds 4 nautical miles, which is more than twice than previously. Once again, the uncertainty of T0 is greater than expected. I will summarize the observations that we are able to make after the first analysis of the results. There is a big diversity of the result between air traffic controllers. Face-to-face speed is less important and low-angle conflicts are more susceptible to errors. The introduction of ND as an uncertainty parameter slightly increases the global speed uncertainty, and controllers seem to take an additional margin of error compared to the 5 nautical miles separation standard. Finally, errors are greater when considering all participants at the same time. Okay, now let's conclude on these results. We saw that the model makes it possible to find the uncertainties on speed, maneuver start time, and heading change in nominal cases. Perception of uncertainties is different according to the controller. Besides, the uncertainty related to the reaction time to complete the maneuver can be determined with this model. The future prospects are as follows. We need to further analyze the quality of the results. We will collect more operational data and try to evaluate controllers on real air sectors. And finally, we want to test an assistant tool with uncertainties calibrating on controllers. I have indicated here some references cited in the presentation. Thank you for your attention and feel free to ask questions.
Yes, so you can use the Q&A button again to ask questions. Thank you, Sarah, for your presentation. We already have a question here immediately by Xavier. First of all, he says, very interesting work, Sarah, good job. Have you been able to perform some analysis around the existing uncertainty in large-scale real-life conditions, trajectories, ADS-B, and how would these real uncertainty estimations find room in your research?
Okay. Hi.
Hi, Nicolas.
Hi. I'm going to help Sarah to answer the questions. She's done a great job until now, and I told her I was going to help her. So we didn't get a chance to get real data, but of course that would be the next step. As you've seen, like our results are not so good, and one of the main problems is that we don't get real data. Like even when we did the experiments with real air traffic controllers on 50 examples, that's still not a big amount of data, and we can't really conclude. What we can observe is that there's a great variability between the different air traffic controllers, and I think that was an interesting result that we won't have if we use ADS-B data unless we know who was the controller and who controlled the situations. So using real data is challenging because we'll get better data, but at the same time we won't have any clue on who was the air traffic controller who solved the different situations.
Yeah, I recognize it. Yeah.
So it would be great if we could have, like, even if it's anonymous, if we could have like this controller is working on this position at this time, and this other day it was this other controller. And I also I'm pretty sure that we would need to have like how heavy the traffic was at what moment, because I guess that the controller's attitude is different considering if there is a lot of traffic or if there is very little traffic, and he could manage to do very good resolutions, or if it's really heavy and then he would have to just get rid of the conflicts. So it would make probably a big difference. So there's a lot of, it's a really challenging problem, and I think that if we can get better data, we can continue working on that subject. Yeah.
Yeah, so indeed, it's just the ADS-B data, because I currently have a master student working on exactly this, for getting this uncertainty out of the ADS-B data. Of course, the uncertainty depends on the predictor, right? So it's not just the data, it's also how you predict it and then compare the deviations. And the ADS-B is, in the end, like you say, it's just a trajectory that was flown, but you don't know what the air traffic controller was thinking, what he was using as a prediction. So what his uncertainty was in hindsight. In hindsight, everything is certain, right?
Yeah, of course. So the thing is that when we observe that there was a maneuver on a trajectory, then we can check the minimum distance looking at the ADS-B. So the track, the real track of the aircraft. And what we can see is that it's almost much bigger than 5 nautical miles, means that there is some margin somewhere. And where does this margin come from? Is it the same for like conflicts between aircraft that are converging, or if they're face-to-face, is it different between conflicts that happen in a heavy loaded sector or in a not loaded sector? So that we can try to find models that, so to give an explanation to this difference.
But sometimes those weren't even conflicts, right? So you get a distribution of minimum distances, but you still have to determine then which parts were solved conflicts and which weren't, right?
Yeah, that's true. Yeah, exactly.
So indeed, a lot of processing. I was also thinking that you consider that the ETCOs, that they maybe also because of their monitoring of the situation, that they might postpone some of the actions to later. So they're willing to accept some risk due to uncertainty and just say, well, wait and see how it develops and then act later. I was trying to look at the time horizon. You define tactical as between 5 and 10 minutes. Was there still time for later actions if the uncertainty proved to be larger than they anticipated, or was there any dynamic effect that you saw?
Well, that was an issue Sarah a little bit talked about was like when we did our experiments in Reims, we didn't really train the controllers to use the time and to like play with the time and go closer to the conflict. And that's why our data were giving us really weird results. So when we did the experiments here in Toulouse with instructors, they were air traffic controller instructors, so most of them have done a real control, and we would really explain that they can like get closer and wait and see and use this thing. But it's still like we decided we decided that an action was taken like let's say 20 to 30 seconds before the maneuver, and then we would see how much time they anticipate on the pilot's reaction. Our model has tons of issues. Like it's probably, you cannot model a human brain using this kind of what we did of simple model. But it has one or two advantages, is that it's simple for air traffic controllers to understand. Like when you tell them, well, you have an uncertainty linked to the pilot's reaction, and we try to model it simply. So it has this advantage that if you want to talk to them and tell them, well, if you want to adjust the parameters and show the red, you see the red part that you should deconflict. Well, maybe in the future, it means that if they had such tools, they could maybe adapt their tool to their feeling of the uncertainty too. So there's a lot we can do. But as you say, solving a conflict is not just like giving a maneuver. Sometimes it's just watching it evolve during time. And because most of among all the 50 conflicts, there were like maybe 10 or 20 that were not conflicts, or even, and some of the controllers would give maneuvers and some others would not. And that was interesting too, because it means that for some controllers, those situations were dangerous, and for others, they were not. And that's in a very like a simple environment. So imagine how difficult it is when you use like the real environment with real aircraft, with all the traffic around, with the third dimension and everything. So
lots of work to be done still.
Yeah,
indeed.
But it's interesting.
Yeah, definitely. Yeah. I find it also very interesting. And also Xavier also comments in the Q&A. He recognizes some of the discussions that also with ADS-B data, it's still not easy to find all the conflict resolutions or the original detected conflicts maybe in the data in hindsight. Are there any more questions from the audience before we close the session? Let me see in the chat, the Q&A. I think there was one from where we discussed this already. No more questions at this stage. Well, then, thank you very much, Sarah and Nicolas, helping Sarah with the answering of the questions. Nice work. And this then is the final presentation of the session. So I'm going to close this session, and I hope to see you all again tomorrow morning or afternoon for the Europeans at 3 o'clock Central European time, 9 o'clock Eastern time, and that's early 6 o'clock in Pacific time. So the advantage that they can do is see a lot of presentations before the work starts, right? And there will be three rooms, then one on ATM performance measurement and management, one on aviation on the pandemic, one of 2 sessions in that room 2, and room 3 on trajectory prediction and trajectory and queue management. So very interesting topics again tomorrow. So we all hope to see you back online tomorrow. Thanks again to the presenters also for sticking to the time, making my work as a chair easy that way. And thanks for this cooperation.
Bye.
See you all tomorrow.